So the last piece of desktop GIS that you need before beginning your projects, or the final aspect of the term, is spatial analysis. And this is where we really start to see the power of GIS as a tool to explore data, create data, make decisions, and solve problems. And I cannot hammer this enough. When you see that red exclamation point, this indicates that the MXD does not know where the data is. So there's a couple things that could happen. One is that you could be looking at the data and the file is zipped. So you can open an MXD that's in a zip folder, and the ArcMap cannot read the data in a zip folder. So that could be the first thing. Second thing, you could have changed the name of the data folder, and I did that in one of the exercises so you could practice reconnecting. Another possibility is that you don't know where your data is. It's in a different folder, you didn't bring it with you, you changed the location of your MXD, or you didn't set relative pathways and now you're working at home. So there's several things to check for that. One program that I like to use is Winzip for most projects, but 7-zip seems to be more robust. It lets you open what's called a tarball, which is kind of a double zipped program. So you might want to download that if you're having trouble unzipping. You might look for that program 7-zip. I find it pretty useful when Winzip won't work. So this is what you might get if you open up your MXD and you have not unzipped the folder. We've had that happen a couple times in class. So I would write a troubleshooting guide. When I get that, what are the steps that I need to take to thoughtfully try to find out what's going on with my data. And remember, you can always open up the properties for each layer, and the properties will tell you where they think the data should be located and what the actual data layer name is. So make sure you develop for yourself a process that will help you identify problems like that. So geoprocessing. Geoprocessing, as I said earlier, is really the power of any GIS application, and this lets you perform some kind of action on a data set that will create automatically a new data set. So remember, when we create a subset, so you're just doing a spatial or attribute query, you can select let's say all of the cities in Oregon that have a population greater than 50,000, and those will get highlighted on your map document, but they're just highlighted, and then you can do a summary, or you can do a statistical process and look at that data. But when you perform some kind of geoprocessing activity, it takes that data and creates an entirely new data set from whatever subset you create, or from the action you perform. This is where it gets to be really important that you know where your data is going, so that you can find it again and make sure you have everything you need. So we're going to look at creating a subset, the reasons that a subset is important. We're going to go through 4 other attributes, or 4 other geoprocessing tasks: to buffer, to intersect, to union, and to dissolve. There are hundreds more, but this is just some real basic actions that are used in spatial analysis. So when you're doing spatial analysis, you're looking at specific characteristics of a feature. Maybe you're seeing how close, maybe you're creating a 1/4 mile buffer around a river to identify the riparian area, and then maybe you're taking that buffer and you're selecting all of the vegetation that's in that buffer so that you can summarize or make a table showing the type of vegetation that's growing there. And you might do that to make a decision about planting. You might do that to think about eradication or restoration along a stream. You might look at the all of the liquor stores that are within a mile of an elementary school in order to predict potential dangers to kids. So using these processes really give you a lot of power. And if you've taken sociology classes, you might have run into Dr. Snow. Dr. Snow is identified as one of the first people known or documented creating a map that was used for spatial analysis. And Dr. Snow in the 1800s in England and elsewhere in the world at that time, there were repeated outbreaks of cholera. And cholera, as we know today, is a waterborne disease often associated with contamination from human waste. But in those days, they didn't know what caused cholera, and they had this theory that it was the miasma theory, bad air, so people would not bathe and they would close their windows and not let fresh air in, and as you might imagine, it exacerbated the problem. But John Snow, during one of these particularly bad outbreaks, he decided that he wanted to kind of figure out where people were who were succumbing to this outbreak, and so he created a dot map, and the dot map showed the location of everyone who had died as a result of cholera. And then he began to analyze the pattern that he saw, and one of the things he noticed is that people living near here were not dying at the rate that people living here. So here, this X is one of the water pumps, and here's another water pump, and here's another water pump. So one of the things he noticed is that the people who were working in this beer factory were not getting sick because they were getting I think a pint of beer or a little bucket of beer every day at lunch as part of their work process. So they weren't going to this water pump to get water. And what he noticed that is people living near this water pump were the people that were succumbing to cholera. So he convinced the city powers that be to prevent this water pump from being used, and the cholera epidemic cleared up. So it's just a really nice, very simple map that was used for epidemiology and for spatial analysis. So the first thing I want to talk about, we did this a little bit in the other labs, is the idea of an attribute query. And the attribute query uses structured query language, or SQL, where we indicate a field, and then we indicate the properties within that field that we're interested in selecting or taking a look at. So it selects records, and each record is considered a row from a data layer based on the value in that field. So I could have a data layer that has all 50 states in it, and each state has different attributes. It might have the name of the state, or it might have the number of children under the age of 15, or it might have the total population. And so in this particular data layer, I wanted to go into the states layer, and the field I was looking for was population field, and then the query was I wanted the number of Hawaiians, so I looked at the population data for Hawaiians over 100,000, greater than 100,000. So that would be one aspect. I might also have a field called city name, and the city name I'm looking for is Springfield. So I could do a query that's a compound query saying, give me all the cities that are named Springfield, and I want the cities with a population over 50,000. So it will only give me the Springfields, because I think I don't know how many Springfields in the US. We could Google that. I think there's more than 7. Oh yes, there are way more than 7. So if you look, I think there were 30 some. Some are cities, some are towns. If you did a compound query that said, give me all of the Springfields and then all of the Springfields that have a population over 50,000, I would get a few cities that hit both of those criteria. So if I select by one attribute, so in the lab, you're going to have a field called Lane schools. So you're going to do some subsetting, and I just want all of the schools that are a type 1. I can say my layer is Lane schools. The field that I'm looking at is type, and then here is my statement. I want selecting from Lane schools where type equals 1. So I'm going to do a query that looks like that. If I wanted to do a compound query, I could do select from Lane Elementary where the school name equals Centennial, or the school name equals Maple, or the school name equals Edison, or the school name equals Centennial. Remember, I have to use or if I want to increase my selection. If I were to use and, my selection would be none, because there is no school name in that same field called Howard and Camp Creek or Howard and Centennial. So typically when I'm looking in the same field and I want to select multiple elements from that field, often or is the correct choice for that. You can also do what's called a spatial query or a location, select by location. And here I am selecting one feature with respects to another feature. In the previous examples, I was only selecting elements within the one layer, and I could select them from multiple tables. So I could have chosen school name equals Centennial and populate or Centennial, or school name equals Clear Lake and school population equals. So that would all be within the same data layer. If I want to look at the difference between two different data layers, then I'm going to use the select by the spatial query. And if there is a location or a spatial component. So if I want to find the liquor stores that are within 500 feet of a school, I could use those two different layers. One would be a point layer showing liquor stores, the other would be a point layer showing the schools, and only those schools that were within 500 feet of or only those liquor stores within 500 feet of a school would be highlighted or selected. I could look at all of the rivers that intersect a road. So maybe I want to do a bridge study or a culvert study. So then I could use wherever the rivers and roads cross, I would find those river sections. Maybe I've got all the schools in Oregon as a point file, but I only want to look at the schools that are within Lane County. So I could use a spatial query that says schools contained in or schools completely in, and then choose from my other feature. So select by location, you still access that from the top toolbar menu using a select, and then I want to select features from, let's say, the school location, and then those that are in Lane County, and then I can put in my distance. So lots of options here. I can also do multiple queries. So let's say I select first all of the type 1 schools in the entire state. So that would be an attribute query, and those get highlighted. And then I do an attribute query that says, now that I have all of the type 1 schools, which might be elementary schools, I want to find all of those schools that are within a quarter mile of a water body. Maybe I want to make sure those kids have safe access or know how to swim. So here I've started off with an attribute query to create a subset of data, and then from that selected subset I've created a location or a spatial query. And you can see what I had to do here was the selection method was to select from currently selected features. So there's another option there. So here is my attribute query, all of those elementary schools. If I can move that over here. And then from my attribute query, I cut down the number of selections because I used a spatial query looking for the schools near the water. So you can see that this point here was selected in the attribute query as being a type 1 school, but it's not close to the water, so it was eliminated from the spatial query. Once I have created a selection, I can take that selection and I can create a completely new shapefile by exporting this to a new layer. And that's something I have to specifically do in ArcGIS and make sure it gets into the right data folder, etc. So not just logical operators of and or are used in an attribute query, but rational operators like greater than, less than, not equal to. And so make sure you know how to set these parameters. So if I were to set a query that says in my population field, I want all the states where the average age is greater than 40, I would use this greater than symbol, but I would not include 40. So you have to make sure you understand, do I want to include 40 or not? If I use less than 40, again, I'm not including 40. So to include 40, I've got to use the greater than and equal or the less than or equal. So you really have to think about what is it you want to do when you create your data. So compound queries we mentioned a little bit earlier. They look, you have to, in a compound query, you need to make sure that the field is listed each time. So if I wanted age greater than 40 and I want income less than 50, I'm going to narrow down my selection. If I say age greater than 40 or average income less than 50, I'm going to get both. I'm going to get all of the attributes where the age is greater than 40, and then I'm going to get all of the attributes where the age is or the income is less than 50,000. So when you do your queries, you really want to make sure, again, you know what it is you're looking for, and then does your query make sense? When you do spatial analysis, you don't have to actively export that data to create a new feature. That automatically happens. So that's a major difference between a spatial query or an attribute query to create a subset. When you get your subset highlighted, you have to take that subset and export it. With geoprocessing tools, a new feature is automatically created, and if you don't indicate in ArcMap where you want that new feature class or that new data layer to go, it will automatically go on your hard drive to a default geodatabase, which is a different kind of data structure that we'll talk about later. So this is where you really have to slow down, make sure you know what you call it, and you also have to make sure you know what you named it, because it will give default names like buffer 1, buffer 2, buffer 3, and if you're trying different buffer distances, you may not remember when you come back the next day which buffer was which. So here, slowing down, checking to know where your data goes, checking to know what you called that when you created it is really really important. So two geoprocessing features of buffering and dissolve are really nice to kind of get a spatial a polygon around data. Overlay is kind of looking at data layers and the relationship between different data layers. So if I create a buffer, so here I've done a attribute query and selected 4 elementary schools by name, and then from those that selection I created a buffer, and I think it's a 1 mile buffer. And so what I will get is a polygon called, if I don't call it anything, it'll be buffer 1 around those schools. And so if I were naming this, I might do school buff 1 mile. And remember, with ArcGIS, you cannot start the name of a feature with a number. So that's why fields and features are called pop underscore 1920. So population 1920. You couldn't do 1920 pop. Buffers are a powerful tool. Here's a buffer that was used after the last big earthquake and tsunami in Japan, and they used different buffer radiuses around the power plants, the nuclear power plants, to indicate kind of areas of danger. Here is a buffer scenario that is really not very effective. There is a buffer created around different nuclear plants in the United States. Red ones are in service, yellow ones are not in service. But the buffer automatically indicates some spatial component, and I think they were just trying to show the difference between commissioned and uncommissioned, and I would have done that just coloring the plants differently. It has a pretty high visual impact, and if I were trying to persuade people that they were in danger from nuclear power plants, this could be pretty effective, because I'm looking at these overlapping buffers, which to me would indicate, gosh, if one of these things blew or if several of them blew, look at the area that would be covered. However, I think this could be considered a propaganda map. I don't know how big those buffers are. I don't know why they have buffers. And in reality, when you're looking at the prevailing westerlies, this section would not be in as much danger as stuff downwind. So But they're common. They're an easy tool to use, and they're very common. The dissolve feature can combine polygons that are the same field. And so in the lab looking at vegetation and zoning, I dissolved the state vegetation data layers so that there would not be so many polygons, because the data file was actually too big to load in Moodle. So I used the dissolve feature, and all of the polygons that were contiguous or touching each other that were of the same vegetation type were then dissolved into one big polygon. And so I take 8 different records, 1, 2, 3, 4, 5, 6, 7, 8, and I'm able to simplify my data into 3 different records. Now, if each of these had a different owner, I've lost all of that information. So when I dissolve, I can only dissolve on one field. And so if my field type is, if the common field here is vegetation type, then I have lost, what kind of soil is in each of those different polygons. So you have to be really careful when you dissolve that you know why you've dissolved. Now, the original data, this is the nice thing about spatial analysis, the original data layer here called input coverage is not impacted. I have not ruined this. My original data layer is still safe. If I've messed up and maybe it's like, oh boy, I really needed to know those owners, I still have that information that I can use. And that's one of the benefits of geoprocessing when it does create its own output file. In the overlay option, I'm looking at 2 different data layers. So with the dissolve, I'm only looking at one data layer. When I go into the overlay, I'm taking this circle layer and I'm putting it over another layer, and my intersect says I want only the physical area or the spatial extent where they overlap. Now the nice thing about this is perhaps this is a large polygon showing oak vegetation, and these 2 polygons are showing ownership. Maybe there's a lot number and an owner name and a property value. The attribute table for my output contains all of the attributes of both data layers where they overlap. So now my attribute will have the owner, the property value, the lot number, and the attribute that indicates the vegetation that was used to create that overlay. So in my earlier example where I created a simple buffer around 4 elementary schools, I was able to take that buffer. I'm going to go back up here if I can find that. Where did it go? So this is just a simple polygon, and the attribute of that polygon is the name of is the attributes that were in the point feature. So if I look at the attribute for this polygon, it will have the name of each of these schools and the phone number for each school and the population. So each of these buffer polygons, these circle polygons, have a different school name associated with them. If I take those buffers and I do an intersect with statewide census data, then I'm going to get the census data that is around that school. It almost acts as if like a cookie cutter in a way. A clip is a much easier function, but now I'm going to get another circle data layer, but what it has taken is the name of the school plus each of these little tiny polygons gives me the number of people in each of those polygons based on the census data. So now I could do a summarize and figure out how many people are within a 1 mile buffer of each of those schools. I could also, depending on how much data is in the census data, I could determine the different ages, the ethnicity, the income, how many housing units, that kind of information around schools. A union keeps all the data. So let's say I have this polygon of vegetation that has one type of vegetation, and I have the two city lots that show ownership, and I do an overlay. I'm going to start out with 2, 3 polygons, and I'm going to end up with 1, 2, 3, 4, 5 separate polygons. In these 2 polygons here in the center where the data overlapped, I'm going to get the attributes of all of both data layers. In this polygon and this polygon, I'm only going to get the attribute data from the original, and in this half a circle here down below, I'm only going to get vegetation attributes. So you'll see in the attribute table there are lots of empty attributes because there's no data for ownership here, because there is no ownership. So that's the overlay function. And then the last overlay is kind of to just look at the symmetrical difference, and it's just a nice way, kind of looks at this in the same way. So the overlay intersect is a way to kind of just get the output here. And then there's other features like dissolve, so many options for geoprocessing that you can use. So the lab will take you through creating a subset, doing an attribute query for a subset, and then saving that as a separate file, then creating another subset, and then creating a spatial subset, a subset based on spatial location, then buffering, then intersecting or clipping, and then doing analysis. So you're going to go through all of those steps to do an analysis project.